Welcome, everybody, and thank you for attending our presentation today. We are going to speak about using a modern data stack to explore and visualize the impact of a global pandemic on aviation. Next slide, please. So we at OnPrem wanted to prove and share our approach to building modern data engineering and analytics stacks. The COVID-19 pandemic inspired us to use our data stack to understand COVID's impact on modern mobility, specifically airline traffic patterns. Some criteria that we chose and that we focused on as we built our data stack were that we wanted to employ best of breed technological components. We wanted the stack to be cost effective and affordable, both upon initial creation, but then also given the modern world of cloud computing and charges as services are used, we wanted it to be affordable as the stack was operating. We wanted the stack to function at scale and to be able to scale effectively across varying orders of magnitude of data ingestion processing. We wanted the stack to be as simple as possible, understanding there is some necessary complexity. And we wanted the stack to be reliable and observable, where observability means the ability to see in detail as the stack is operating what is going on and under the hood in the various components. One of the challenges in building a stack, and when you are not already starting with existing data and you want to do it to build an MVP platform or to demonstrate how to do things, is finding a good data source that has data that's at scale, at volume, that's updated, and that's relevant and interesting. We found the OpenSky network, which provides an API that gives the location of a significant fraction of airborne commercial aircraft at any given time. Next slide, please. So OnPrem Solution Partners is a technology consultancy. All of us presenting today are part of the data and analytics practice, and we will go one by one and introduce ourselves.
My name is Yasha Maradi.
My name is Justin Simmons.
Hi, I'm Josh Huntley.
And I'm Josh Andrews. I am the principal of the practice and our lead. Next slide, please. So we have two goals today. We want to share our principles for architecting modern data stacks. And second, we'd like to visualize and explore the pandemic's impact on aviation. Next slide, please. So I'll hand it off to Yasha here now to give you a background on what's been happening in recent history.
Yes, we just wanted to give you a quick recap, just going over some of the news headlines that came out in the last few months. Just to go over, give some more context for what we're going to be talking about. So at the end of 2019, it was essentially business as usual for the airline industry, and the regular year-over-year growth was predicted. And great tidbit in that conference that they had at the end of 2019 is that we were connecting more cities than ever, and China was leading the development in that area. Airlines were hiring, and they were giving away free tickets. By the end of January, airlines were taking notice of rapidly growing outbreak in China, and they started thinking about different ways to cut flights and take care of bleeding revenues. By the end of February, the airlines were dealing with outbreaks in multiple other countries, and the coronavirus was quickly sweeping the entire globe. The cost to the airlines was at that point around $30 billion, which was the entire profit that was predicted for 2020. In March, COVID-19 was officially recognized as a pandemic by the World Health Organization. And some of the airlines were some of the first casualties of the coronavirus, and by that we mean that the airline went bankrupt and went out of business. And fast forward to today, and you will essentially see a business model in jeopardy for the airlines and them scrambling to figure out how they're going to take care of their business going forward. So a dark time for aviation is about to get darker. I'll hand it off to Josh H.
All right, thank you. So over the next few slides, we'll be discussing our vision for data stacks. And before we get into that, it's really useful to understand where that vision comes from and what it is a response to. As consultants, we have the opportunity to see a large number of organizations up close. And as a result, we've become familiar with the challenges that are commonly faced by our clients. And really, our vision is a direct response to these challenges. Some of the challenges that we see very frequently on the technical side are scalability of data ingest and processing. Sometimes systems are architected for tens of billions of rows, and suddenly they're dealing with hundreds of billions or more. Maintaining known good state of systems and version control, testing data, again, readdressing the economy, making sure that the systems are practical to run in economic terms. A lot of clients have this vision of near real-time data ingest and processing. We want to avoid deploying or developing platforms and tooling where possible. There's plenty of good databases on the market. Why try to rebuild something that's already there and available? And we want, a modular data stack. We don't want to have to worry about adding or subtracting pieces and having that affect the rest of the stack. And then on the staffing and organization side, we think that focusing on SQL is a great idea. It's easier to staff and it's easier to train for those skills. And there's currently a user expectation for rapid changes and updates. We're looking at a time frame of days or weeks rather than months or years. So with this in mind, let's look at our vision for what a good data stack looks like. And we'll do this in terms of the diagram that's used in our current MVP environment. So this is the overall diagram, and we'll just kind of move through some of the key points following the data as it flows through this diagram. Next slide. So we believe that all systems should be resilient to errors, and this really starts with data as it arrives in the system. We're proponents of the ELT approach. We think data should be ingested in as raw a state as possible. And this way, any kind of bugs that are in our transform logic can be fixed in the future without permanently affecting the source in any way. And we just reprocess that source data with newer updated transforms. Next slide. So next, the technologies themselves. Technologies in general should be scalable, flexible. There should be minimal infrastructure to upkeep. There's plenty of very mature infrastructure as a service technologies now. They've matured significantly, and they always are. And it prevents the opportunity to maximize the value-added work by our data engineers and offload this infrastructure maintenance component to vendors in the marketplace. And the newest technologies also allow the opportunity to abstract storage and compute in ways that allow the two to scale independently. So we're no longer worried about the size of our hard drives versus the size of the compute nodes. Next slide, please. So some common major pain points in data engineering are source control of data processing scripts, testing, and alerting. And data engineers are fully capable of writing custom code to address these items, but really selecting tools which provide these features off the shelf allow our internal data engineers to focus on the highest value projects with confidence, knowing that the work that they're doing is value added with related to the specific data rather than related to kind of rebuilding functionality that exists out in the marketplace. We're looking for tools that have version control, integrated testing of both configuration changes and data quality and errors, and that are CI/CD friendly. Let's move to the next slide. But finally, the stack should be easily usable by a variety of data consumers. Once the data is built, the data models are finished, they should be accessible and easy to join to and query. The overarching goal here is that we want to collapse this division between thinkers and planners and doers and allow really any of our internal customers who have a good idea to flesh that idea out and analyze the data in a way that makes sense and that is intuitive. So that's kind of the overall vision, and I'm going to hand it off now to Justin.
Thank you, Josh. Before we go too far into the implementation of our vision, we wanted to give a quick overview of the development pipeline that the tools in our vision enable. There are two environments, Dev and Prod, which with matching long-standing Git branches. So updates to the environments are made via pull requests. Data loading, processing, and testing takes about 90 minutes every night in each environment. Snowflake is a cloud data platform that does abstract the compute and storage into what they call warehouses and databases respectively. This allows us to independently scale the compute for each operation, and we can do so in seconds by altering the size of the Snowflake warehouse. Next slide, please. Starting with the developer workflow, development begins by creating feature branches from the dev branch. The developers are able to query the data directly, as well as pull down the code base, which they can run using dbt locally, but still utilize the storage and compute of the cloud database. This is possible because running the code locally with dbt only compiles the configuration to transformation code, and then connects to Snowflake to actually run the commands. Any work that they do only affects the development database and only uses the computing power of the developer warehouse. When they're happy with their code, they submit a pull request to the dev branch for the team to review, which gets merged into dev after a review process. Next slide, please. The code in the dev branch is scheduled to run on a regular basis by dbt Cloud. For this project, we're running the jobs on a nightly basis, loading incremental models 6 times a week with a full weekly refresh, which is a full drop and load taking place on the weekend. Once the code has been successfully running in the dev environment for some time, the code can then be promoted to production by merging dev into the master branch. Next slide, please. Similar to the development environment, the master branch is executed by dbt Cloud to populate the production database, which we then present to the data consumers. The data consumers also use a separate warehouse, not shown here, to access production. Separating development, ETL, and BI tool warehouses means that one process cannot overload another. They can be scaled independently, and the compute costs are automatically allocated to each process. Next slide, please. Here's a brief overview of the implemented architecture before we go into the extract, load, and transformation pieces in more detail. We have lookup and streaming data being stored in S3, which is periodically queried by Snowflake and transformed into staging and analytics models that are defined in dbt using jobs that are scheduled and orchestrated by dbt Cloud. The process is fully automated with the exception of infrequent updates to mostly static lookup data and the periodic loading of analytics tables into our BI tools. Next slide, please. Moving through the architecture left to right, we'll start by an introduction to our primary data source, the OpenSky network. Next slide, please. The OpenSky network gives us a collection of aircraft states containing information such as identity, latitude, longitude, velocity, and direction at any point of time through an API. On the right, you can see the OpenSky network coverage as of early January 2020. Clearly not complete global coverage, but still gives us a good number of data points to analyze. Since late 2018, we've gathered about 2 billion, closer to 2.5 billion unique points after deduplication. The API is pulled every 30 seconds and saved as files to a location where they can accumulate over time. We'll be covering this in more detail as well as discuss the form of the raw data when we cover the extract and load process shortly. Next slide, please. So conceptually, how can we take positional data and aggregate them into flights? First, we need to clean up the raw data from the OpenSky network, which results in about a 50% reduction in points. We are then able to group these points together by using their flight number and aircraft identifier, and then implementing timing and altitude logic to the points to label takeoff, cruising, and landing sections of a flight. These collections of points can then describe flight legs, where a flight leg is defined here as an airplane traveling from one airport to another without stopping. We then take the first and last points of each flight leg and match them to the closest airport using the haversine function, which is a function that estimates the distance between 2 latitude and longitude coordinates, taking into account the shape of the Earth. Now, this function can be non-performant when trying to do a full cross-join between all of our flight endpoints and all of the airport coordinates around the world. So before we use this function, we filter out all airports that are outside of a 1-degree box around the endpoint. We can then take the flight legs and group them together into flights, which consist of one or more chained flight legs that share the same flight number with an acceptably short layover. Next slide, please. Here we can take a look at the points of a typical flight leg. We see the collection of points that represent a flight with the geographic location shown at the top and the altitude of each point shown at the bottom over time. The OpenSky network is a terrestrial network, and there are gaps in this coverage as we can see with the break-in points over Kansas. As you can imagine, this also results in flights that travel over large bodies of water, having large periods of time without any reported points until they appear over land again. So our grouping logic needs to be able to handle those cases as well. Next slide, please. Next, we'll take a look at the takeoff and landing points for some flights. The map on the left shows the Burbank airport and takeoff points collected by many outbound flights. And the map on the right shows the same airport, but plotting landing points of inbound flights instead. The outbound points on the left are much more spread out, which makes sense. Once an airplane takes off, they can head towards their destination. When an airplane is landing, you expect them to be much more lined up with the landing strips. Now turning over to Josh A., who will continue discussing the architecture.
Thank you, Justin. So one of the things we wanted to do with our architecture, particularly given that we are not doing change tracking or anything else where we need to track internal state in our database, is we wanted to use S3 as our backing store. So we don't actually have any special or unique data that is separately stored in Snowflake. We can literally truncate our Snowflake environment and rebuild everything from S3. And we periodically do this just to make sure that everything is in sync. We do, as has previously been mentioned, focus on an approach using an ELT, so a lightweight approach with ephemeral data loaders or ingesters with minimum amount of change in ingest. Most formatting, filtering, changing should be happening in the database given the now low cost of storage. Streamsets Data Collector is a good example of a lightweight ingest component, and that is what we use to pull the streaming API from OpenSky. And our current cost constraints don't allow true streaming all the way through the stack. Snowflake costs are the largest. Part of that, if we really truly wanted to implement near real-time processing in Snowflake, that would be significantly more costly than what we've currently done. But because of the way we've architected the solution, we could go back and do that in the future without having to entirely redesign and rebuild everything. Next slide, please. So we pull the OpenSky API for positional flight data every 30 seconds with Streamsets. We could pull it as often as every 10 seconds if we wanted to, but we don't. We flatten out the API response and write it to S3. And the API response, while it is JSON, there's really not much of the way of hierarchy to it. So it's pretty simple to write out. And then we actually use dbt to pull the S3 data in periodically, both the raw flight API streaming data that we've ingested and the lookup data as well into Snowflake. Next slide, please. So with the data available to Snowflake staging tables, dbt is then used to handle the transformations to generate the rest of the models. Data is finally written to analytics tables for exposure to data visualization tools. Nightly jobs pull in data from S3 and process it in Snowflake with incremental changes. We do a weekly full reprocess in both dev and prod. Dev is limited to the last 3 months of data to reduce costs and development and testing times. We intentionally wall off the staging areas from end users. And if needed, we can reload and reprocess all data at any time. And now I'll hand it off to Josh Huntley.
Thank you. So we've mentioned dbt a few times. Next slide, please. I'm looking at 31 here. We've discussed dbt a few times. So before we go any farther, I think it's useful to have a discussion about what it actually is. dbt is an open source tool for authoring, testing, and orchestrating data engineering pipelines. And if you look at this diagram on the bottom, the boxes in red and the boxes in teal are really what dbt handles. So the boxes in red are kind of its primary functions. It snapshots, transforms, tests, deploys, and documents data natively in SQL or YAML files. And then these boxes in teal are the things that kind of additional functionality that are very useful. So it integrates nicely with version control systems such as Git, and it offers native alerting and logging features as well. And this, going back to our vision, these are really core, cornerstone pieces of our vision. Because the snapshotting, transform, test, deploy, and document flow is so easy, it allows our data engineers to focus on much more value-added things. And what we'll do next is look at our data engineering process in terms of the logic, using our DAG, or the directed acyclic graph, which represents our data transformations, as the template. Next slide. So here's the full DAG for our environment. On the left, you'll see these tables in light green. Those are our raw input sources. And data flows through our system, and it ends up at these tables on the right, which are our finished star schema, dimensions and fact tables, which are exposed to end users. And these tables in the middle somewhere, those represent data as it's being transformed through various steps of logic through our process. And those steps typically include, towards the left here, right after our raw data, kind of a source-conformed set of tables that are cleaned, and the columns are renamed into our final nomenclature, and any data errors have been handled. And then you can follow this DAG through. We have one of our final tables highlighted here on the bottom right. And when you highlight this table, you can see its full lineage, all the ancestor tables that are feeding that. dbt does this for you automatically and natively. And as a developer actually writing some of these tables, it's very useful to be able to visually see all the different places where data are coming into a given step. So I know this is fairly zoomed out. So next slide. So we'll go ahead and zoom in on this little table right here, just to see a closer picture of our DAG. And you can see how everything is connected here. We have our external raw tables flowing into some staging tables, and you can see we're actually spinning out some of our dimensions fairly close to the beginning of our DAG here, because it makes sense in this given context. Next slide. So again, going back to our overall vision, why do we do this? Why do we use dbt? It's so that when we're presenting information to our end users, that information is in a clean and business-ready format. So we can connect really any kind of tool to this, or we can give more power users the ability to connect via SQL clients and do more powerful transformations. So from here, I think it's useful to talk about kind of the approach to our modeling. And to do that, I will pass it off to Yasha.
Cool. Thank you, Josh. When it comes to modeling the data, there are many, many different ways of doing this. One of the ways that we specifically like to do this exercise is by following, getting inspired by Kimball's methodology of breaking down the data and tables into facts and dimensions. One of the reasons there are many reasons why we do this. We've listed some of them here. The main one is that this process tries to kind of model the data after real life and how the processes and the entities that actually exist out there, rather than trying to model the data based on some sort of back-end structure that was put in place by somebody who was trying to optimize the system versus optimizing processes and analytics. This is designed with users in mind, so we try to make it as easy as possible, try to reduce the number of heavy joins or difficult joins that could be potentially made. And one of the biggest advantages of this model is that it is extensible. And you're going to get to know what I'm talking about in just a minute. So as they explained, we bring all of this flight information into our Snowflake model, and we do all of these transformations to then finally arrive at this particular star schema. What you're seeing is that there's a fact table in the middle that contains many, many events. In this particular case, it's going to be a list of flights and all their attributes. And then all of the tables surrounding it that are linked to it, those are what we call dimensions. They're essentially lists of entities, of business entities. You can break down facts by dimensions. So that same dimensional model that we showed you, this is a particular BI tool. So this is Power BI. Virtually all the analytics we did for this talk, we did it in Power BI. So you can see that the data model, the star schema that we were mentioning to you earlier, essentially comes to life inside of the BI tool as well. So the user doesn't have to go and manually create all of these tables or join them together. The joins are predefined by us. So in order to do some of our analytics, we actually brought many other data points as well. As you know, the name of this talk is how the pandemic has affected aviation. So we had the aviation data, but we also had to go grab the pandemic data and other data sets as well. Nowadays, there are services and tools, for example, BigQuery or Snowflake. They all have public data sets, which make different kinds of data sets available to the public. Great. So this is essentially the full analytical model. So the previous model that we showed you was just for one subject area. So for instance, looking at flights or looking at pandemic or looking at different parts. But at the end of the day, because the way that this has been modeled, dimensional modeling, all of these facts and dimensions link together to let us do our analytics in a more efficient manner. So the big takeaway here is, even though you see many tables on here, you can really just break it down by facts and dimensions. So all the facts are at the bottom and all the dimensions are sitting at the top. So with that, let's dive into the data a little bit. So our story begins on January 11th. We didn't want to go too far back. We thought January 11th was a good point of context. And that's basically the day that Chinese authorities sent the genetic sequence for what we used to call the novel coronavirus 2 to the World Health Organization. And at that point in time, we had about 22,000 outbound flights captured by the Open Sky Network and then transformed by us and captured. So fast forward 1 month on February 11th, and that's when the World Health Organization officially named the disease based on protocols that they follow. At this point in time, even though the number of cases are increasing, air travel does not seem to be slowing down. And in fact, if we just look 1 month prior to January 11th, when we started this story, there has been about 6,000 more flights since then. What we're going to try to do now is, because these flights fluctuate daily, we're going to take a moving average because this measure is much less sensitive to daily fluctuations, so we can see overall trends over longer periods of time. So when we take the moving average for this year and we compare it to last year, we see that even year over year, air traffic is still increasing. And that's what was expected if there was no pandemic going on. So you see two graphs here. The bottom graph just showing the number of flights per day that we capture in total. And then the top graph is visualizing the number of cases on January 22nd and increasing all the way up to February 11th. So you can see that there's been an explosion of cases in China. At that point, there were other countries that were getting infected too, but the majority of these cases, the bulk of them, are actually in China. So just to give some more context, when we look at these numbers in terms of growth, there's linear growth and then there's exponential growth. So in this particular case, we're looking at this as if it was a linear growth. And you can see that in just a matter of 20 days, the number of cases grew by about 8,000%. So it went from 555 to about 44,000 or 45,000. And at this point, also other countries were getting infected as well, and the number of cases were going up in those countries as well. The number of countries that had a case actually increased by 4.5-fold between January 22nd and February 11th, which is a very short period of time. Let's try to visualize the exponential growth of COVID-19 cases and deaths. So we're going to place that on a logarithmic scale. People who are not used to this sometimes often have a hard time trying to digest this information. But one of the key takeaways is that if you see a straight line on these types of graphs, it basically means that there is exponential growth happening to that particular measure that you're looking at. So you can see here by February 11th, there were already 1,100 deaths total, and the number of cases was still exponentially increasing. When we look at air traffic, we still don't see any signs of slowing down. So flights are still taking place. People are still traveling. They're going to vacation and many other places, work. We forward 1 more month, March 11th. This was the day that the World Health Organization officially declared COVID-19 a pandemic. And you can probably see why. The number of cases and deaths are, again, exponentially increasing. At this point in time, governments began ramping up restrictions and banning travel and other measures to try to contain the virus. So at this point is when we can see that the outbound flights begin to kind of flatten out. And that's the day that the US suspends most of travel from Europe. That actual ban took 2 days later on the 13th. So in order for us to combine our data with other data sets, so for instance, we downloaded mobility data from Google, who uses people's location tracking data on their phone who have opted in to try to count the number of visitors to particular locations, for example, workplaces, transit stations, grocery stores, or pharmacies. But for privacy reasons, Google doesn't actually give you the counts of those visitors or how many people are there. What they do give you is a % change from a particular period in time that they use as baselining. So the idea is that you go to a time before the pandemic, but not too far back, and you try to kind of designate that period as pre-pandemic levels, right? And then you try to calculate the % change from that level kind of going forward. So as you go down, once you come back up to 0, that's when you basically return to normal levels. So what this slide is showing is we're doing the same thing that Google is doing. We're taking the period from the 3rd to the 6th, and we're essentially arranging all of these days, and we're doing it by weekday because we know there are fluctuations throughout the week. So for every weekday, we take the median out of all the days in our population, and we use that as the baseline. So when we do that, here's an example of what the baseline looks like. So you can see that it's periodic by week, and then we actually do that subtraction and to try to get the % difference. And what you'll notice is that we essentially end up with the same pattern as before, but now everything's been transformed into percentages, so now it can be combined with other information. One piece of information that we wanted to pull in was general passenger numbers of passengers. So here we see TSA checkpoint travel throughput that's beginning to rapidly fall versus 2019. And you can kind of see that that is happening. The number of passengers is rapidly falling by 22%, even before the number of flights are going to fall. So then we forward one more month into April 11th, and this is when the big hit kind of takes place. You can see that the number of cases and deaths are rising rapidly. Cases are rising 13-fold, the deaths are rising 25-fold, and what is falling are flights. So we're 69% lower than that pre-pandemic level baseline that we defined. And the TSA passenger numbers are 95% lower than what they were the prior year, that same weekday. So let's take a closer look into the flights. So I've filtered right now just for outbound flights. You can see that the percentage to the baseline is on the y-axis and months on the x-axis. Let's just kind of keep the moving average and get rid of the noise so we can get a better look. I'm going to kind of dot this and make it blue because we're going to lay other measures on top of this so we can keep track of the actual change in airline traffic. So the month of May is actually when the minimum drop has been reached. So it seems that recovery is going to be on the way, but there's still a dark road ahead. Recovery begins for most. However, some collapse and become history. So here we have 2 examples of 2 airlines that actually went bankrupt and stopped operating by April 11th, or by May. By May 11th, they actually had no flights. So by April 11th, that was basically their last flight. However, when we look at cargo airlines, it's basically business as usual for them, even a modest increase. So they virtually go untouched. And I think we all have a pretty clear idea of why that is. Some other nuances that we wanted to look at was that are airlines changing the way that they operate because of what's going on with the coronavirus and the fact that they cannot fill their entire capacities. So for example, for American Airlines, we went and pulled one of their hubs. So Dallas-Fort Worth is one of American Airlines' hubs. You can see that back in April, they actually started utilizing this hub more than all of the other airports that they utilize. So the measure we're using here is we're essentially looking at how many flights did American Airlines do out of this airport versus how many flights did they do in total that particular day. And then we do the division to get an understanding of utilization. So that's what we mean by utilization. It's just how many flights were in this airport versus all the airports for this particular airline. We see something similar with Southwest. their hub. This is one of their hubs, Chicago Midway International Airport. And you can see in a similar fashion that there was an increased utilization of this hub back in April. That sharp decrease that you see between April and March is actually, there was an outbreak at the airport, so they had to shut down the entire place for disinfection for a few days. One other nuance that we wanted to also look at, we wanted to know, are the aircraft themselves flying in any sort of a different manner? So we looked at flight altitudes, and we didn't look at all the altitudes. The idea we had was you can basically take the maximum altitude for a particular flight, and that should give you a pretty clear idea of the type, how high that flight was going, and that should also correspond to the cruising altitude. So you can see that there's a marked increase in March. That's basically when all the flights dropped. So it seems that as there are less people on flights and there is less flights in the air, it seems that the airplanes and pilots can actually fly higher in order to preserve fuel efficiency. So just to explain a little bit more on that, a normal commercial flight does a process called the step cruise. So the majority of flights for commercial aircraft are spent in the cruise section of the flight. And as they're going through and burning fuel, the aircraft's actually getting lighter. So it's more fuel efficient to actually go and fly at a higher altitude where you have thinner air, so you can get better fuel economy. So our idea was that because now flights are empty or half empty, or at least in the beginning of the pandemic, that was the case. Airlines actually are trying to fill up their full capacity now. But in the beginning, many of the flights were not full. So we thought that either the airplane would start at a higher altitude to cruise to begin with, or throughout their cruise and step climb, they'll actually end up at a higher altitude. And those data points can also be seen in the data as well. And with that, I'll hand it back to Josh Andrews.
Thank you, Yasha. So just to give everybody a final bit of information about OnPrem, we've talked about how we built our data stack, some principles around it, and then told a story around how we used the data to verify, validate, and understand what's been going on this year. We at OnPrem are 230 plus people. We're 100% onshore. We have 3 consulting locations in Dallas, Los Angeles, and New York. We have 1 software development center in Austin. We have 7 areas of expertise, of which data and analytics is one. We also help our clients in areas such as digital media supply chain, IP management, customer experience and CRM, PMO and project management, custom software development, and AI and machine learning. And our growth is 100% organic, no acquisitions. Our client base, Fortune 200. So what do we help you with data and analytics from our practice? Well, we have aspects of strategy that we often start with clients. Doesn't have to be, but it often starts this way. Architecture assessments, solution evaluations, data governance, data profiling, moving into really the meat of data management, ingest pipelines, storing and warehousing the data in platforms like Snowflake or BigQuery, modeling the data, dealing with data quality issues, sometimes talking with your teams upstream, master data management, making sure that we've built it in such a way so that we can do continuous integration and continuous deployment and automated testing. And then finally, of course, the business output, analytics and visualizations, dashboards, KPIs, semantic layer modeling if needed, self-service analytics, eventually predictive analytics. Next slide, please. So thank you for coming to our presentation. If you want to know more about us, go to onprem.com. And, as Richard Branson said, and as we found, if you want to be a millionaire, start with $1 billion and launch a new airline. Thank you very much. And we will take questions now.